You see two red vectors there. Physically, you might see this as there's an object that appears, say, at the one point that we see the eta plus minus square root of 3 qualia or particle can suddenly reappear on the other end of that semicircle there. And so they would call that quantum tunneling. It relates to particles appearing and disappearing when you go down to the microscopic level of the space-time fabric, for instance. So, there's lots of quantum effects there. Another one in standard model also has the electroweak interaction or the electroweak theory. And arguably, that's the most difficult one to understand when you're doing physics coursework because it's not very intuitive about how they describe it. But the confluence between the spherical component, which is that circular arc, and where it bends back into the hyperbola, the angle between the white axis and that point at that eta plus minus square root of 3, that's what they call the Weinberg angle, or the ideal for it, which is equal to pi over 6, which is 30 degrees. It's such an important angle in physics where it gives rise to massive bosons and the ratio between them. And it all relates to the Higgs mechanism and how particles take on mass to begin with. And so they can't explain where the angle comes from. The theory is called the Petit Salam theory. They came up with it and it seemed to work. And so a lot of physics is like that, where it's guesswork, where they try different things. And that's the angle that seemed to work. By working in the angle space, or from what we say from the standpoint of light, we start to see geometrically what it involves and why it is as it is, and how physics sees it that way. The approach bears fruit immediately for the physics of it all. And once you see this cohesion where one thing leads to the other, how they're all interconnected, I think it opens up this landscape for physics to progress beyond stalemate with where it's at currently with the standard model in particular.